Hi guys, so in this video we're going to solve RLC circuit problems using the Laplace transform, instead of the normal differential equation method we're used to before when learning them in the time domain. We're now going to use the Laplace transform to take functions to the S domain, solve, and bring them back. So that's what we're going to be doing in this video. Straight to work. Our first question, it goes this way: find V0 of t in the circuit, assuming zero initial conditions. This is a very important thing to note. There are zero initial conditions. So I'll explain when we solve. Alright, so this is U of t, our voltage source is U of t, 1 ohm resistor, 1/3, a third of a farad capacitor is dividing the circuit in half, and then a single Henry inductor is over here. So the V0 of, this is supposed to be V0 of t. Okay, so the V0 of t that we're looking for is the voltage across the inductor. Alright, so let's get to solving and see how that affects. Let me quickly change this to V0 of t. Remember, we're doing the Laplace transform, alright? Meaning we're going to be moving from the time domain to the frequency domain. What that means is that we're going to need to redraw the circuits in the frequency domain. So since we're told there are zero initial conditions, that means all the elements are going to be exactly the same. No new element is going to be added. If you had certain initial conditions, governing components, then other components will be needed to add it to make sure the voltage and current laws still apply. But we'll do that in later questions. Okay, for resistors is the same. So we have 1 and 5 here. The Laplace transform, you can look at, we covered this in the previous video, looking at the table and pointing out the transforms of different expressions. So the Laplace transform of the unit step function is 1/s. So here, instead of U of t, since we're in the time domain, since we're in the S domain, okay, let's highlight this. We're in the S domain. Don't forget we're in the S domain. So this voltage source is now going to have a value of 1/s. Laplace of the capacitor, so that's a third of a farad, is going to be 1/sc. Okay, as 1/s times 1/3 raised to -1, which is 3/s. So this is going to be 3/s. Alright, and the Laplace of our inductor has 1 Henry is going to be SL. So that's S times 1, which is S. An important thing to note, what these values are. What is 3/s? What is S? What are all these? These are what you call impedances. Okay? Impedances. When you deal with Ohm's law, remember V is equal to IR, which is simple, short. It makes sense. Alright? Gog ohms. This is this principle. When you come to the frequency domain, the complex domain, it's exactly the same relation, but voltage is now I times Z, where Z is your complex impedance. Okay, so the same relations you have when you're dealing with normal time domain circuits, normal resistors, V equals IR, it's still going to be the same thing here, where Z is now our impedance. Alright, so remember previously, there is no way we could have found voltage across this directly with algebraic multiplication. Okay, the voltage across an inductor in time domain is L divided T. Now it's simply I times the complex impedance, which is the beauty of the Laplace transforms. So let's get to solving problems to see how we can actually make the most of this. Okay, what we're going to do is mesh analysis. Loop 1, so this is I1. Loop 2, I2. Let's get to work. I have lots of problems to solve. Let's see how fast we can go. Okay, I'm taking for mesh 1. Okay, so for mesh 1, minus 1/s plus I1, that's 1 times I1, plus 3/s I1 minus I2 equals 0. Because this is this way because we're solving for mesh 1. Alright, so we have a component in between two loops. If we're solving for mesh 2, it would be I2 minus I1. Okay, what are we trying to do? Isolate I1. Alright, let's see how that goes. So that's going to be I1 into brackets 1 plus 3/s minus 3/s I2 is going to equal 1/s. This is beautiful and elegant. This is where we stop for. This is where we stop for mesh 1. Okay, solving for mesh 2 or loop 2, actually anyone. Okay, let's have, this is S. So SI 5. Oof, my handwriting. That's 5, not S. I need something else fishing. Sorry, guys. Okay, so that's 5I1, 5I2, okay, plus SI2 plus 3/s I2 minus I1 is going to equal 0. We have 3 terms of I2 here. Let's see if we can bring that out. So that's IT S plus 5 plus 3 over S minus 3 over S, or is equal to 3 over S I1. Let's do it this way. Simple, short, and elegant. If we're to make I1 the subject of formula, we're going to multiply 3 by S and divide by 3. That's 1 over 3 S squared plus 5S plus 3 IT is equal to I1. Beautiful, elegant work. So we're going to throw this guy back into its expression that we got for loop 1 and see how that pans out. Okay? Oof, that looks really fun. 1 plus 1 over 3. 1 plus 3 over S, pardon me, times 1 over 3 times S squared plus 5S plus 3 I2 minus 3 over S. This keeps looking like a 5. Okay, minus, let me erase it. Did I erase it? I erased the box. Minus 3 over S I2. Okay. Is equal to 1 over S. You might get tricked into jumping and solving this, but an advice tip, an expert tip is try and eliminate fractions as early as you can. So you can see our common denominators are S3, S and S. So we're going to multiply everything by 3S. Okay, multiplying this by 3S, 3 cancels out. We get S out. S is going to multiply this guy. So that's 1 plus 3 over S. These guys are going to get an additional factor of S. I need to write my factors better. Plus 3S. IT minus 9. It should be 9. I2. Okay, so that's minus 3 over S times 3S minus 9 I2. Okay, it's going to equal 3. Since we must find this by 3S. Okay. Algebra. Expanding this bracket, we're going to end up with, okay. Firstly, the terms will repeat themselves since we're multiplying by 1. S cubed plus 5 S squared plus 3S, then multiply by 3 over S. Okay. What's happening? Okay. This is S, not 5. I kept thinking this was 5. 3 over S. So we have S here. So S is going to do a lot of justice to this term. So 3 over S times S cubed is 3S squared. Okay. Plus 3S plus 3S squared. Is that correct? Okay. Plus 15S plus 9. 15 plus 9 all into I2 minus 9 I2 is going to equal 3. Okay, we can see 9 I2 minus 9 I2. So this 9 is going to go. Trying to simplify this, we're going to have 3 is equal to S cubed plus 8S squared plus 18S I2. Or I use small letters. I2. Okay. Making I2 subject of formula. I2 is equal to 3 over S cubed plus 8S squared plus 18S. This is a really huge milestone we just crossed. Okay. We're now able to express the current through this loop in complex variables. But recall, we're looking for voltage as a function of time. Remember Ohm's law, V is equal to ZIZ. Okay, IRIZ. So now we're going to multiply this. This is our current. Multiply this by the impedance. All right. So recall that. Recall that V naught of S as voltage as a function of S is equal to SI2. All right. So we're going to leave us with V naught of S is equal to, multiply this by S. All these guys will lose an index of S. So that's 3 over S squared plus 8S plus 18, which is really amazing. All right. What we have to do now is to factorize this equation. Or you know what, let's solve it. Partial fractions. See if this is to polynomial 1, 8, 18. Okay, it's complex. So let's solve it. Let's factorize now. So I'm going to solve this question factorizing, and the other ones now solve a partial fraction. So in case we get stuck, let's say we don't want to solve a partial fraction with complex roots, then we'll just go straight and factorize. What do we do? Our denominator is s squared plus 8s plus 18. The coefficients of s alone. So this is b. Our quadratic is plus. Ooh. Okay, I made a mistake. Ax squared plus bx plus c. All right, so b for this is 8. So b over 2 is going to be 4. All right, so this 4 is going to be our crucial point to start off. So now we're going to have s plus 4 all squared. Expanding this gives you s squared plus 8s plus 16. And you see then we were just 2 off from our original denominator. So now we're going to add 2. Simple and short. So our new denominator is going to be s squared, s plus 4 all squared plus 2. But we're trying to factorize, so we need to make this a perfect square of something. So this is going to be root 2 all squared. All right, simple and amazing. We can throw this back in. Let's throw this back in. So that's going to equal 3 over s plus 4 all squared plus root 2 squared. Really amazing and beautiful. However, when you look at the Laplace table, whatever is being added to s has to be the numerator. So for there to be a clever workaround for that, we're going to do v naught of s is going to be root 2 over root 2, then multiplied by this. Okay, s plus 4 all squared plus root 2 squared. So what this is going to do now is that we can now bring 3 this way. This is really, really, really cute math. So we're going to bring 3 this way and bring root 2 this way. So now we have a constant that can come outside our Laplace transform, right? So v naught of t is going to be the inverse Laplace of 3 over root 2. We could bring that out actually, times root 2 all over s plus 4 all squared plus root 2 all squared. We're essentially done with most of the work. You know that 3 over 2 is going to come out. So v naught of t is going to be 3 over root 2. We're going to take the inverse Laplace of this function. All right, so that's going to be e to the negative 40. Then of the entire thing, it's kind of like the chain rule. So that's going to be, since there's a constant here and here, so that's sine root 2 times t volts, provided that t is greater than or equal to 0, which is really, really beautiful. So I hope you're able to get what happens when we solve the Laplace transform. In this one, we don't have initial conditions. So the first thing we do is transfer from time domain over here to s domain. Okay, find the equivalent impedances for each of them. Solve analytically as we would do normally in the time domain and get the necessary complex equivalent of that expression. We're finding v naught of t, so we get b naught of s. If we had to find I of t, we'll get I naught of s. That's the whole reason we even chose I2 in this case, then multiply with the complex impedance s. Okay, so we do that. Then, do some nifty manipulation to make it look like something that has an easy inverse Laplace transform, and then booyah kasha. Alright guys, I'm excited. Question 2. Determine v naught of t assuming 0 initial conditions. If auto required, 5 u naught of t amps, 1 Henry, and v naught of t. Now we're looking for the voltage across our resistor, 4 ohms. Okay? Assuming 0 initial conditions. So now we know this is our time circuits in the time domain. So we know our circuits in time is going to be exactly the same as our circuits in the frequency domain. Let's get to work. Drawing this guy in the complex domain. Okay, the Laplace is a really amazing machine. Okay, 4 ohms, V naught a singular, pardon me, okay? We're working in time domain. It's not going to be the same values, 5u of t. Or how do I keep writing the time equivalent? Alright, guys, so recall we are going to, isn't it same with you not? We're going to have to find the complex equivalent of these guys. Okay, so our resistors, it's going to be the same. So this is still going to be 4. Okay, the Laplace of u of t is 1 over s. So this is going to be, 5 over s. The Laplace of capacitors is 1 over sc. Okay, so that's going to be 4 over s in this case. Alright, the Laplace of an inductor is SL. So that's 1 Henry again, okay? So that's going to be S over here, simple and short. And we're going to find the 5 over S. They're really out for me with this question. 5 all over S. Or should I start writing my S in cursive? 5 over S. Alright, so what we're going to do now, we're looking for this voltage, V0 of t. A really amazing thing we're going to do now, we're going to use source transformation. Okay? It's an elementary, we could use source transform in the time domain. We can still use it in frequency domain. So we have it's like a Norton equivalent, transferring a Norton pair to a Thevenin pair. So once you have a current source in parallel with a load, you can use Ohm's law to get the equivalent voltage source in series with that load that will have the exact same equivalent. What am I saying? V is IZ. Okay? So the voltage V Thevenin is I Norton times Z. Let's kind of think of it that way. So since we have 5 over S, this is our I Norton, and we're looking for V Thevenin. So VTH is going to be 5 over S. I'm seriously sorry. I need to write 5s more deliberately. 5 over S times our complex impedance times 4 over S, which is 20 over S squared. So now this is exactly going to be identical to a voltage source, 20 over S squared, coming this way. We can now place our load, 4 over S, alright, then draw as we would normally for current source. No, you just source transformed. That's a good catch, okay? I believe we're good. Is this good? Yeah, I have a good feeling about this. So now that we source transformed, we have a singular loop for das currents, for the current to flow. And we can do a very nifty I. Let's try and write cursive a bit more. So we have I. What are we going to do now? Regular source transformation. So start with this. 4 over S. 4 over SI. Okay. 4 over SI plus IS plus 4I is going to equal 20 over S squared. Multiplied by S. Right? Let's get rid of this guy. Okay, so that's 4SI plus SI. Is this IS? Yes, this IS, as in doxalic. 4 over SI plus SI plus 4I is going to equal 20 over S. Okay? And most likely with S squared. So we end up with no fractions. S squared. No, this will be regular S. So 4 over S. You know what? Let me start again so as to not confuse anyone who's watching. I kind of got sidetracked. Okay? We're going to take the mesh analysis to the loop. Okay? The first we know the means 4 over S. So 4 over SI1. Okay? Next one. I of God. Okay? Plus SI plus 4I is going to equal 20 over S squared. Okay, because it will be minus 20 over S squared equals 0, then taking to the other side. equal to 20 over s squared. Multiplying through by s squared. Okay, so we're going to have 4, and take this up. 4si plus s cubed I plus 4 s squared I is going to equal 20. Let's bring I out. S cubed plus 4 s squared plus 4s is going to equal 20. I is going to be 20 over s cubed plus 4s squared plus 4s. Amazing, right? Recall what we did. V naught as a function of s is the same as zi. Okay, so that's going to be a complex impedance is 4. So 4 times I, which is 4 times this whole thing. So V naught of s is going to be equal 80 all over s cubed plus 4 s squared plus 4 s. Amazing. Partial fractions. Okay, partial fractions. I believe we can bring out something here. S, so that's s squared plus 4s plus 4. When we factorize this, okay, that's minus 2 twice. So V naught is going to equal 80 over s plus 2 squared. Pretty amazing stuff. Partial fractions. Do you remember partial fractions? That's what we're going to use to solve this. We have a repeated root. Okay, so that's, I really like writing vertically. Okay, we have a repeated root. That's s plus 2 all squared. So we'll have a constant. Okay, we're looking at all the things in the denominator. The first one we're going to tackle is s. Okay, so that's going to be a over s. Okay, we're going to go a term lower than this. This is s raised to power 1. So our numerator is going to be s raised to power 1 minus 1. So this is a constant, a. So essentially, if your factor is s squared, your numerator should be, say, bx plus c. Essentially, if your denominator is x cubed, your numerator should be, cx squared plus dx plus e. Is e the next letter? Okay, so with our repeated roots, we do b over s plus 2 first, then c all over s plus 2 all squared. How I do this is that I multiply both sides by the denominator so we can clear everybody out. So we're going to multiply this by s plus 2 all squared. So this is going to be just 18. So a over s times s plus 2 all squared is going to give us a s plus 2 all squared plus b s plus 2 plus CS computer science, I believe. This is a really cool trick now. So we're going to set s to be equal to minus 2. Why are we doing that? If we set s to minus 2, this is going to be minus 2 plus 2. This guy goes to 0. This is going to be b times s times minus 2 plus 2. This goes to 0. And then we're set left to just cs. So that's going to be 80 is equal to minus 2c. Right? So therefore, c is equal to minus 40. Pretty elegant. If you're thinking ahead, we can do the same thing for 0 now. So you have 2 terms with s, so we can set s equals 0. Set s equals 0. So we're going to have 80 is equal to a into 2 squared. So that's 4a. So that's a is equal to 20. We have 2 terms now. We're now going to need to expand so we can get the last term. So that's 80 is going to be equal a s squared plus 4s plus 4 plus b s squared plus 2s plus cs. Okay, I'm going to bring out the common terms. S squared is going to equal a plus b. Okay, s is going to be 4a plus 2b plus c. Alright, then plus 4a is going to be 80. Simple and beautiful. What's the last time we don't have? B. Okay, so we're going to compare the coefficients of s squared here and s squared here. Nothing. So 0 is equal to a plus b. Oof. 0 is equal to a plus b. A is equal to minus a is equal to b. So b is equal to minus 20. Pretty amazing stuff. So now our fraction is going to look something like 80 over s into s plus 2 all squared is going to equal, what was a? 20. So 20 over s plus, since b is minus 20, minus 20 all over s plus 2, negative 40 all over s plus 2 all squared. Let's start again. All squared. So recall this is v naught as a function of s. So v naught as a function of time, you guessed it, is going to be the inverse Laplace transform of v as a function of s. So that's going to be the inverse Laplace of these guys. 20 over s minus 20 over s plus 2 minus 40 over s plus 2 all squared. A cool property of the transform is that, it's the same as taking each of these guys independently. Okay? Plus, so in case you get stumped by the repeated terms. Okay? S plus 2 all squared. Really amazing. We've covered this in the last video. Since all of these, we know the inverse Laplaces of all of these from the tables. Okay, so we're just going to go and write a final answer. So that means v naught of t is going to equal, this is 20 over s, 20 of t. Okay. There's going to be minus 20 e to the minus 2t minus 40t e to the minus 2t volts. If you want to factor and look cool, what can we bring out? We can bring out 20. Then we'll take out minus t2. So that's 1 minus e to the minus 2t minus 20 e to the minus 2t e of t volts. Ta-da! Oof. Oh my. How do I get rid of this? I just draw an S box. Okay. E of t volts. Say it again. So ta-da. Same mistake. Okay, but essentially, okay, and the more serious is, so this is how we use the Laplace transform to solve circuit equations. You can see it's not as daunting and complex as it seems. Alright, so in the next video we solve 2 more questions.